All right, so the problem statement says, given an n by n matrix in the form of a two-dimensional array made up of binary integers where ones represent obstacles and zeros represent empty spaces, we have to find all the possible path combinations that avoid the obstacles from coordinate 0, 0 to n comma n, right? So here we have an example right here, and it says it's a 2 by 3 grid, and we have to start, our starting position is here, and we have to get here. So we have to calculate all the possible positions, or all the possible paths to do that. So one path would be from going from here to here, and that's one path. And that's the only actual path we can make, because this one acts as an obstacle. We can't go here, because once we get here, we hit this obstacle, and we can't go any further from there. And here's another example. The output in this example would be 6, because we're starting here and we have to get to here. So we would go, one path would be like this. Another path could be like that. Another path, you get the point. And you can go down, and then that would add up to 6 total paths that you can do with this one. Because we have these ones blocking, we can't go there at all. Okay. All right, so we're going to be writing a depth first search function on this matrix. So we have to first declare what our boundaries are going to be and our base cases. So a boundary that we have to make sure we don't cross will be, so if the n, which of course will be the size of the rows, the amount of rows, and m will be the amount of columns. If n equals the grid dot size, or m equals the grid at index 0 dot size, right? That's just matrix logic. Then we will return a 0, meaning the path is no longer good because we just stepped out of bounds of our matrix, right? And then another base case would be if we find a 1 within our matrix, which is an obstacle. So it's a little bigger. So if grid at n m equals a 1, in that case we also return a 0 as not a valid path. But if it is a valid path, meaning we reached the end, so if n equals the grid dot size minus 1 because of indices, or no, and m equals grid at index 0 dot size minus 1. So we reached the end of the grid, so we're happy with that, and we can return a 1 as in that was a valid path that led us to there. Okay, so this n is 2 and m is 2 could be viewed as this little diagram, okay, where our starting position 0, 0, 1, 1, and we start here, and we'll say this is a 0, this is a 1, 0, 0. And we're trying to get here while we're here. So there's actually only one path we can go to, and that's this right here, just like that, because we can't go here because of the 1. So if we were to draw a recursion tree to represent this, we would start out with 0, 0. And we have two different options. We can either go left or right, incrementing n or incrementing m. And if we increment n, in this case, we'll go 1, 0. If we increment m, we'll be at 0, 1. Okay, and then once we do that, we check our base cases. Now, our base cases, remember, if the grid at mn, so if the grid at 0, 1 is equal to a 1, in this case it is, we're going to terminate right there, because that can't lead to a good path. So this would actually just return 0 back up to its parent, just like that. And then we come down this branch, and now this branch, we can either increment n, which would be 2 comma 0. But this right here would hit that base case that n is equal to the grid dot size, so n is equal to 2. So this right here would also return just a 0 because we're out of bounds of the actual array. Notice how it's 0, 1, there's no 2, so this coordinate doesn't actually exist. We just return 0. Or if we go down this path, which is the 1 comma 1 path, right there, we can return our 1 comma 1 is the end of the path, so we can actually return 1, meaning we got there, which will return 1 to here, and then this would take the sum of 0 and 1, which would be 1, and returning it back to its parent, giving us an output of 1 plus this 0. So the total combinations of this matrix from getting from here to here would be 1. And that's kind of how it would work. Alright, so now since we understand the algorithm, we can finish up the code here. So assuming that the function of this would be declared by an int, we'll call it DFS, and it's given a two-dimensional vector, so vector of vectors of int, and it's called grid, and it's also given an integer n and an integer m. So if our function is declared like that, we would simply just, after all these base cases, we just return, and we would return the sum of DFS, give it the grid, n plus 1 and m plus the DFS of the grid, of course, because the grid stays a constant the entire time, of n without the plus 1 and the n plus 1, changing the incrementations to traverse the grid. Right, so the time complexity of this algorithm is indeed 2 to the nth power. If you haven't seen my last video, I went into more detail of why that was. But if we wanted to optimize this, we can obviously optimize it with memoization, storing a DP array, which has stores all the duplicates that we find within the tree and cuts off those branches that we don't need.